Hello, this is Ms. DB, and today we are going to go over Chapter 9, Section 6 on modeling real-world data. Our objectives are to apply functions to problem situations and use math models to make predictions. This is very similar to other assignments that we've done, except we have added more types of functions that we can check and see if our data fits that. And we're going to be using Desmos to do this, and we'll be using their nonlinear regression equations. Well, some of them might be linear, but we're going to use Desmos in order to do this. There are other options out there besides Desmos. There is the TI-84 graph, or TI-83 graphing calculator is able to do regression. Regression is when you enter in the data points, make a graph, and then you find the function that fits it best. There's also some other online-based calculators out there. But Desmos works really good. It's got a really nice graph that goes with it, so I like that one the best. All right, so the data that you encounter in the real world may form a pattern, and lots of times we are able to model that pattern, fit that pattern with one of the functions that you have studied. If you find the function that fits the data, like it's exponential or quadratic and the particular numbers that go in there, then you can use that equation in order to make predictions and to analyze trends and to find out what's going to happen maybe in the future or maybe in the past. All right, so here's some of the different kinds of functions that we've already talked about. And linear, you learned that in Algebra 1. Quadratic, you probably were introduced to that in Algebra 1, and we spent a whole chapter on it in Algebra 2. And then the same thing with the exponential and the square root. We spent a lot of time learning about those kinds of functions. Now, if you want to tell whether some data fits one of these, one thing that we can do if we don't want to graph it and run regression is we can look at the table of values. We can generate our own table of values, or we might be given one. If the first differences between the y values are the same, then it's linear because the slope is constant. So up 1 over 1, up 1 over 1. If the constant second differences, or if the second differences are constant, then it's quadratic. If the ratios between the y values are constant, then it's exponential. And I don't know if we've ever talked about this one, but if you have the second differences for the x values are constant, then that's a square root function. Let's look at some examples. Okay, so here's a table of values already given to you, and we want to decide whether or not this would be linear or quadratic or exponential or square root. So it looks pretty clear to me. Well, first of all, you check the x values. So the x is going up by 5, by 5, by 5, by 5. So they're increasing at a constant rate. That means we can go ahead and check the first differences. So that means that you take 93 minus 58, and whatever you get, you put here. And then you take 128 minus 93, and you put that difference here. If those are all the same, then it's linear. So here are those values just written by themselves, and we're going to subtract them. 93 minus 58 is 35. So 93 minus 58. 128 minus 93 is also 35. 163 minus 128 is 35. So if you find that the first differences are constant, then you don't have to check the second differences or the ratios or anything else. We can say that this is going to be a linear model. Now, this doesn't give you the equation, but it lets you know then what to work with to get the equation. All right, so in this one, the first differences are not going to be constant. The x values, though, they increase by 4 each time. So the first differences we can subtract. And here's what we get for the first differences. Negative 400, negative 384, negative 369, they're not the same. When we check the second differences, that's when you subtract these two from each other. They're also not the same. So if the first differences are not the same, it's not linear. Not linear. If the second differences are not the same, then it's not quadratic. Now at this point, you might want to graph it and get an idea of what it could be. Or we can move on and check the ratios. So the ratio is when you check 9,600 over 10,000. and then you check 9,216 over 9,600. Those are the ratios. So let's check those now. They're constant. And if they're all the same number, that means they're constant, then that means that you have an exponential function. And again, this doesn't give us the equation, it just gives us what type of model will best fit the data. And then we can use regression to find the exact equation. And here you can tell it looks almost linear, but if you were to zoom out a little bit, it would be more clear that this was exponential decay. It's decreasing more rapidly than it looks on that little piece of a graph. Okay, let's check this one. So first we look at the x values and make sure they're increasing at a constant rate. And if they are, then you can check the first differences by subtracting 165 minus 132, and that's 33. And then 154 minus 165 is going to be negative something. So the first differences are not going to be constant. This is not linear. Then we check the second differences. And this time the second differences are constant. That tells us that this is a quadratic. We can also generally tell if it's quadratic if it increases and then after that it goes up and then after that it goes down, 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 down. So it's going up and then down like a quadratic function would do. Again, you can look at a graph just to kind of verify, and it does look like a quadratic. Okay, to check this one, the x values are not increasing at the same amount like all the other ones did, but the y values are increasing at the same amount. The only one that this works for then is the square root function. So the square root function is different than the others. In the other ones, the x values are all increasing at a constant rate, and the y values, either the first differences or the second differences are constant, or else the ratios of the y's are constant. But for the square root function, the y's are constant. These are each increasing by 10. And then we look at the x and see what they're doing. So here's the x values. The differences are not the same, but the second differences are same. So if the second differences of the x values are constant, then this is a square root function. Okay, here's one more example. X values are increasing at a constant rate. The y values, let's see, let's check the first differences, not the same. Second difference is not the same. So then we move to checking the ratios, the 324 over 243, and the 432 over the 324, and the 576 over the 432. And they're all equal to the same decimal number, 1.333. So that, therefore, this is the exponential function. And that one, you can't tell that that's exponential. It's increasing at a very rapid rate. It's exponential growth, I think. Let me go back and look at the table. Aren't these growing? Yeah, this is exponential growth, not decay. Typo. All right, so you got a good idea about how to check from your table and tell whether or not you have a exponential growth or decay. Now let's look at what if you have real-world data and you actually need the equation of the function that best models it. So first we'll go ahead and we'll do what we just did. In this one, if we call this x, the x values all increase by the same rate. That throws out the square root function. The y values, let's check the first differences. 70 minus 10 is 60. 175 minus 70 is not 60, it's bigger than that, it's 105. And so on. Get your calculator out, subtract these, see what you get. The first differences are not constant. Now we check the second differences. They're also not constant. So therefore, it's not going to exactly fit a quadratic. However, where's my calculator? I'm just going to calculate. You'll see, I'm going to do the ratios, that these aren't going to be perfect either. 70 over 10 is 7. The next one would be 175 over 70. 175 divided by 70 is 2.5. And then we have 312 over 175. Oops. 312 divided by 175 is 1.78. These are not close together at all. So this is true for most real-world data, is you're not going to get an exact fit. This is not going to be 100% quadratic or exponential or linear or square root. However, the second differences, 45, 32, 51, 30, they're pretty close together. They're not exactly, but let's look back at our graph. I know that doesn't tell you much. It looks kind of quadratic, but we can't tell for sure. So what we're going to do is we're going to run regression to find which model best fits it. Now we're going to start with quadratic, and if the R value is close to 1, then it fits it pretty well. But I also would probably check exponential in this and see if it fits it better. Now they're quadratic. They did this on their graphing calculator, and they got that the R squared value is 0.9999, which is very good. It's almost 1. So what you do then is you write the quadratic expression y equals ax squared plus bx plus c, but for a you put in this number, and for b you put in this, and for c you put in this. Now this is very similar to what we're going to do in Desmos, or you are welcome to use your, if you have a graphing calculator, TI-83 or TI-84, you may use that as well. In this one, the x values are every 2, so the y values we're going to check the first differences. And the first differences are not constant, and they aren't really very close. The second differences are exactly the same. So this quadratic function is going to be even better. It's exactly quadratic, and we get that r squared equals 1. So then for the a you put in 0.5, for b you put in 2.5, and so on. Very good fit. So they're not always going to be evenly spaced out x values. Like in this one, we go from 90 to 93, that's plus 3. But then we jump to 97, that's plus 4, and then plus 3, and plus 2, plus 5. So it's going to be hard to find the first differences and the second differences because we don't have evenly spaced data for up here, the x values. You could try to pick out the ones that are evenly spaced. Let's see. But we're going to have gaps. So instead, let's just go ahead and look at the scatter plot. And for our scatter plot, we're going to use technology to make ours. We'll enter our data in, and it looks like that. And then we're going to decide whether it's quadratic, cubic, exponential, or so on. And we're going to see which one has the best r squared value. So the first one's quadratic, the second one's cubic, and the last one's exponential. They're all really good. The one that's closest to 1, the r squared value, is going to be the one that we'll pick. So it looks like exponential is a little bit better, and we will use that one as our best fit. Now we're going to be using Desmos to do our regression, or I am. Again, you're welcome to use your graphing calculator if you can. I've made a video before on how to do regression using Desmos, and you can watch that video again. This was from our chapter 7. So in Desmos, these are the different models that we're going to try for linear, quadratic, cubic. We haven't talked a lot about cubic, but that was in the polynomial section. It looks something like this usually. Exponential, the natural log, we did a whole section on logs, and the square root. So these are the different things that we'll type in to check which is the best fit. All right, so here's a couple different graphs. And there's some questions on your graph too where you'll check the, you just have to look at the first differences, second difference, and so on. But I want to get to the ones where we actually are going to use Desmos. So I'm going to quick write down, as I'm going to be switching between a couple different, I'll just open the worksheet. Okay, so here's our calculator, Desmos. Move it over a little bit. And there, now I can see both parts. Okay, so I'm going to go to the plus sign, do a table, and I want to put in these values. So the first point is -2, 8. Whoops, 8's up here, not down here. And the next point is 0, 10. And you just enter all of these in. You can use your keyboard, or you can get the keyboard down here if you need that one. 2, 8, 4, 2, and 6, -8. And then I'm going to look at it first, and I'm going to see if it looks like it's quadratic or linear or exponential or so on. So let's move this over, and I'm going to zoom out just a little bit. Oh, it looks quadratic, doesn't it? Doesn't it look like a parabola that's opening downward? So I'm going to run quadratic regression first. And over here, let's see, make that really little, is the quadratic regression thing. Stay over there this size. Okay. Okay, so I'm going to type in the Y1, and you can just type a 1 after it, and then you type that little squiggle key, which on my keyboard is way at the top left corner, and then I need A times x1 squared. Okay, and then I need plus B times x1, and then plus C. And you can see, even before I make my graph bigger, that it has graphed that purple line right on top of my dots, and the r squared value is exactly 1, which means that this quadratic function fits our data perfectly. So now I'm ready to, you're supposed to copy this and put it over here, and then I'm going to write the equation, which I can't do because I'm in, I was going to type it in Word, and this is not Word. So where's my pen? Here we go. So this is y equals something x squared. I have to look back at my graph to see what it was. Plus something x plus something. So now I got to look back at my Desmos, where'd you go, Desmos? Here it is. So it was y equals -0.5 x squared plus 0x plus 10. So this needs to be -0.5 x squared plus 0x plus 10. I don't really need the 0x. Come on, right. Which I would just write as y equals -0.5 x squared plus 10. And then you're supposed to also paste your graph that you made in your Desmos. And to do that, you can take a screenshot of your graph. It might be nice for you to include in your screenshot the regression that you ran on it. So I'm going to take a snip, and I'm going to just grab this whole little part, and then I will copy it, and then I would paste it into the worksheet. So here's the worksheet. The actual worksheet might be easier just to use that. So then for number 5, I could just paste the graph right there. It's quite large, doesn't need to be that big. I just need to be able to see it. And then your equation, you would type that in there as well. We already wrote it in the other, was it -0.5? Yep, -0.5 x squared plus 10. Since b is 0, you don't need to write the x term. There you go. That's how you're going to do these problems. You'll do the same thing for 6, 7, 8, 9, 10, and then we get to some real-world problems. Now, when you do these, they're not all going to be quadratic. Some might be linear, some might be square roots, some might be exponential. So you're going to have to run different kinds of regression to find out what type might fit it best. Let's look at number 8. Let's do number 8 using Desmos. So let me move this over. open up my Desmos graph again. And I'm going to turn these off. And I'll just delete them. And make a new table. And these are my values to enter. So I need 0.06, which goes with 0.2, and then 0.375, which goes with 0.5, 0.96 goes with 0.8. And it looks like this is an interesting one because the y values are all increasing at the same rate, and the x values are not constant. So my guess is that this is going to be the square root one, going from what we looked at the beginning of this video. These are all the y values are all increasing by 0.3, but it's not linear because the x values are not all increasing at the same amount. Whoops, 1.4. Okay, so now let's look at this graph. And we'll zoom in because it looks so little. Yeah, that does not look like a linear function, does it? It's curving. It looks like a square root function, which is what I'm guessing it is. If you're not sure, though, you can run some different kinds of regression. Maybe you think that it's exponential. So here's all of my list of the different types of regression that I can run with Desmos. Okay, so I'm going to start with, let's say that I think that maybe it's exponential. So I'm going to type y1, and then is similar to, and where did I go? A times b to the, and you can use that little caret, and where are we? x1. So the exponent is x1, x sub 1. Let me move my graph over so you can get a better look. So it's not fitting the data very well, is it? It's curving the wrong way. And you can see that the r-squared value, it's 0.8. It's not horrendous, but it's not very good. It's not 0.99 like we kind of want. So let's try a different regression. I'm going to turn off this black one, this exponential, and let's try another one. All right, so for this one, I want to try the square root function. So again, y sub 1, so you just type y1, and then is similar to square root. Now, for the square root, where do you get that function in Desmos? I think we need to open up our, sorry, it's not staying put where I want it to. We need to open up our keyboard here. Show the keypad, because over here there's some different functions, and we might find what we need there. And we see there's different square root functions here. However, there's also a square root key, so I just need that. So I'll use that. But there were some different things there if I couldn't find what I needed. So I need the square root of a times x sub 1. And then I check, yep, that looks good. Okay, so now let's see, let's hide my keypad, and let's see if that fits the data better. Oh, it fits it very well. It's this orange line. It goes right through my data points, and r squared is equal to 1. There's only one value I need to put in when I copy this equation over into the worksheet, and that is that a is 0.666667. So let's get a new snip, and I'll just take a picture of this and go to edit copy. You probably have this on your computer as well if you don't have another screenshot type of a program. And then here's my worksheet, and this was for number 8, I believe. So I'm going to paste this right here, and then I can put the equation right after that. It might be a little easier now that I have the information already there. So y is equal to 0.666667. Oh, it's supposed to be the square root of 0.666667x. And there you go, your equation's done. When you get down to the real world problems, it's really the same thing. You're going to graph the data, put your graph here. Then write the equation that models the data. You might have to try a couple different things like I just did. And then you're going to use your function or graph to predict something. So if you're looking at a graph and you need to make a prediction, like in this problem here, like if I wanted to predict what would be the y value when x was 4, you can click right here and you'll get a value. So at x equals 4, y is equal to 1.6333. Or if I needed to know when will y be equal to 2, let me make this a little longer so I can see. When will y be equal to 2? Maybe it's going to just approach it and never quite grab it. Maybe I want to know when y will be equal to 1.5. And then that is right here. Really close to there anyway. Right, you don't have to have exact. It's at about 0.997, or maybe it's even at 1. So when y is equal to 1, x is equal to 1.5. Okay, so finish the worksheet up. Let me just go back to the PowerPoint and see if there was anything else we needed to go over. But I think that was pretty much it. You're going to finish making your scatter plots, find the equation that best models it, sometimes make predictions on using your graph and your equation. Thank you very much, and let me know if you have any questions.